Okay, we can start. Good morning, good evening, and good day to all, and welcome to the internals session about the physical structure of tables. Thank you for attending the Data Platform Summit 2020 and joining my session. I want to open with a simple question so you can ponder about your answer while I will introduce myself. The question which I want you to answer is this: is the order of columns important? And you can see the example of creating two simple tables with the same structure except the order of the columns. Today, we will discuss simple row store tables, and we will focus on data that is stored in line. In addition, we will not discuss express columns. This means that the server treats the row as one entity. If the server needs data from the row, then it must read the entire row from the disk to memory. Just to remind you the basic structure of rows on the disk, this can help you to answer the question. The data of the columns is divided into two groups. In one group, we have the data from all the columns with fixed length size, one after the other. In a different location in the row, in a second group, we have the data from variable length column. So the physical order does not necessarily fit the order which we created the columns. This is one of my last physical event before the corona, which I spoke at. Unfortunately, today, I cannot get your answers directly since we are limited to online meeting. Therefore, I will present several common answers which I collected from different forums. Feel free to read and select your answer. Now, I want to clarify that by important, I mean important for performance. For example, can the order impact performance when we will use the table in the future? Or is it possible that using one order over the other, we might encounter errors while we will execute the exact same query? We can split all the answers into two groups. All the answers which say that the order is important came from developers. Their main interest was the order that columns returned when we use simple queries like select star, meaning when we select all the columns without specific order in the query. In this case, the columns return in the order that we created them. But this is not relevant to performance, and I'm asking about performance and the point of view of a DBA. In the other side, we have answers which came from expert DBAs. This include Microsoft Data Platform MVPs, top supporter in the forums, and even someone with more than 500,000 reputation points in Stack Overflow. From my experience of asking this question, I assume that most of you agree that the order of columns cannot impact performance. Am I right? I think that this is a good time to present myself while you think about the answer to the question. My name is Ronen Ariely. I'm a senior consultant and an architect. I work in the field of application developing and data platforms. My main focus is on designing enterprise-level platforms. And what I really love is to dig into the internals. This means to examine the undocumented level of the product and implement it for practical uses, like improving performance. And this is exactly what we are going to do today. This session is pure demo intensive session. The only slides which I have are for the introduction and for closing with a summary and some tips. If you have questions during the session, please feel free to use the chat. Let's go straight to the SSMS, and we will start with checking the answer to the opening questions. Okay, for the sake of the demo, I will create two databases. And in this script, I basically create a new table and execute several queries, including insert of 10,000 rows. At the end of the script, I present the size of the data in the table and the size of the two new databases. Okay, notice that the server used about 5,000 pages in order to store the data, and the database has grown to 144 megabytes. Now let's change the order of the columns and execute the exact same queries on the second database. Wow. Did you expect to get this result? Notice that the server used double the number of pages in order to store the exact same data. The database size has grown to 272 megabytes, and all we did was changing the order of the columns. Until the end of this session, you will understand what happened here and why. Let's examine another case. Again, I create a simple table and execute several queries. We can see that it was executed without any issue. But the question is, what will happen if I will change the order of the columns? How can it be? I'm using the exact same queries, but for some reason, using a different order of columns result with an error. Clearly, the order of columns is important. What we should do next is to understand why this happened, and more important, how to prevent it from happening in our production. And this is what we are going to do in the next 50 minutes. One sentence about theory. SQL Server manages internal hidden physical layer while exposing to the users a logical layer. All the following queries, select from table, using system table, using built-in store procedure, and other tools are exposing only the logical layer. In order to examine the physical structure, which is not for the simple user, I will need to use two undocumented entities, sys internals partition and sys system internals partition columns. Using those system internal views, I create a function that returns the information about both the physical and the logical structure of the table. Now, each time that I will change a table, I only need to execute the function in order to get the information about the new structure. Let's go over the basic structure that we have right now and understand the function. So object ID, index ID, partition names, number, and column name, pretty much clear. Partition column ID. This is the logical order of the column. leaf null bit, this is the physical order of the column, max data in length, max data total in row and out row, key ordinal, this is the order of the columns which participate in the key, and leaf offset, which is a value that give us the position for fixed length column. And for a variable length column, it only gives us the order of the columns. So 4 bytes mean that this column start after 4 bytes, which is just after the headers. -1 means that this is a variable length column and it position in the first place in the second group. What we are going to do during the demo is to change the table in different ways and compare the physical structure before and after the change. My first change will be to add a primary key. Okay, note that by default, when I create a primary key, then a clustered index will be created for us if there is no cluster index already, and if we did not explicitly define the column as non-cluster index, as we have in this example. We can see that the index ID changed from 0 to 1, since now we have an index. In addition, the value of the key ordinal column changed to 1 in the column that participates in the index. Let's remove the key and check if this cleaned the table. Okay, we are back to the original structure. But what will happen if I will create a key on a column which is not the first column? Or maybe I will want to create a primary key on multiple columns. So let's go to a bit more complex demo. Since we did not explicitly create a cluster index, creating the primary key automatically created the cluster index for us. Notice that the physical order of the columns changed. The columns which are related to the clustered index are in the first position. We can also notice the order of the columns in the key ordinal values. So, what happened behind the skin? Did the server move the columns inside the row? To answer the question, let's examine the binary data on the disk before and after I will add a clustered index. In order to examine the data on the disk, we can open the data file in hexadecimal editor like Notepad++. Or we can use 2 additional built-in undocumented tools. Those tools are much more familiar than the first two which I used before. The first tool I will execute using the command dbcc-ind. This command returns all the pages which store data that is related to the table. We need to get the number of the data page for the sake of the next step. Next, we will use the command dbcc page to examine the data on the disk. This command returns a lot of interesting information about the page. For now, I will skip the headers and the statistic and go straight to the data. Here we have information about each row in the page. In each line, the tool presents information about 20 bytes from the disk. The first information that we have is simply a running number telling us what location we are looking at. The second information that we have is the actual binary data as it is on the disk, presented in hexadecimal. And the third information that we get, this is an interpretation of the data, an attempt by the tool to convert the data into readable value. If the data is simple English text, then it succeeds to present it. Notice the order of the data. My name, Ronen, appears before my family name, Ariely, which fit the order of the columns. Let's add a clustered index. Okay, so what changed? The table has new column with null as name and partition ID 0. This new column is totally hidden from the simple user, but it is a real physical entity with 4-byte size. The developers who execute queries on the logical layer see the same order as before. They have no idea that the table was changed and it's bigger table at this point. Notice that the leaf offset of the new column is negative, like variable length column, and it located first between the variable length column. This column includes a unique identifier which has the size of 4 bytes. It is added when we create a cluster index without using the unique property. When we created the primary key, then this column was not added since primary key is unique. The order of the columns also change. And we can confirm what happened in the binary value that we have on the disk. First of all, you can notice that the page number was changed. This means that everything was copied to another location. The data is stored in a different location on the file, and now you have a proof that adding or changing a clustered index lead to copy the entire data in the table. We can also watch the data itself. And check the order of my name. It used to be Ronen Ariely, and now we have Ariely Ronen. Order of columns changed. What will happen if I will try to remove the new index? And you can notice that the hidden column did not drop. It is still there. We are stuck with this structure with a bigger table, at least for now. What about adding a non-clustered index? Notice that we have two physical columns added with the new index ID equal 2. The first one includes the data of the column which we used for the index. The second one, using the null as a name, is a hidden column that includes the unique identifier information from the clustered index. Can we reclaim the size of the non-cluster if we will drop it? The data on the non-clustered index is not part of the table. Therefore, removing the data does not require changing the table. The server has no problem to do it. In fact, the server does not delete anything, but simply change the metadata, while the data of the index stays on the disk and ignored. Here we can see a demo adding few indexes with multiple columns and include column. We can summarize the behavior with 2 sentences. For each column in the index, we get another column in the metadata structure. 1, 2, and 3. And we have a hidden column for each identifier and a column that participate in the cluster index. 1, 2 in our case. And let's not forget to add a primary key separately from the index. Check how complex our table structure became simply by manipulating the table. Creating a primary key added another third index ID. I think that it is already clear at this point that each time that we change the table, multiple new physical columns might be added to your table, which many of those are totally hidden from the users. What will happen when I will rebuild the index online? When we rebuild index online, another column is added with the parameter isAntimatter value equal 1. This parameter is used for the procedure of build of the index, while antimatter rows will be created during the procedure. At the end of the index build, the new column will stay and we will stuck with it in the table structure for now. What is the impact of enabling change tracking? Again, another new column is added to our structure. And notice the leaf offset. This column includes 8 bytes. Let's play with a variable length and see how they behave. First of all, I want to change a fixed length column to a variable length. SQL Server need theoretically to move the column from one group to the other. The leaf offset of the column change from positive 12, which is a fixed length position, into minus negative value, minus 2, which means that this is now in the variable length group. What happened behind the skin is that the column was dropped and a new column was added at the end of the variable length. Now let's change the variable length to make it bigger. So in this case, I increase the size from 20 to 100. Notice that increase the size was done in place. Nothing changed except the max in row length. So what will happen about the opposite side? Let's decrease the size back to 20. And this is strange. This is exactly the opposite behavior than a fixed length work. In variable length, decreasing the size dropped the column and created a new column at the end. In this demo, I want to test what will happen when I take a column with the data type Unicode UTF-16, and I will change it to use simple text like varchar. This fits to a situation that you move your database to SQL Server 2019, for example, and you want to use the new feature UTF-8 instead of the old data type using the UTF-16. So again, we see that what happened behind the skin is dropping the column and creating a new column at the end, at the end of the data length. A very simple demo. Let's speak about partition table behind the skin. I create a partition function and partition schema, and now I can have a table which is partitioned. If you will check the structure of the table, then we can see that we basically get 2 row sets, one for each partition. And this is identical to working with 2 tables. Behind the skin, the physically structure is like having 2 tables, but logically, they are managed as 1 table. As I said at the beginning, this session is intensive, and I assume that following online meeting is not so simple task. I remind you that you can use the chat for questions or you can contact me after the session. At the end of the meeting, I will summarize some of the main points regarding the changes in the physical structure as a result of different actions. In addition, this session is recorded and I will publish all the sample code online. I think that we are ready to the next part of the meeting. After all, understanding the internals is not a goal, but a means to a better understanding in order to get better performance in production. Now that we already saw the impact on physical structure on the table, we want to move to the second part of the session and discuss real life and real case scenarios. And for the first case, I want to bring a question from the MSDN forums with a nice request. This question led to a very interesting discussion with multiple experts and multiple solutions were suggested. The story is like this. We have a very big table which include big int column. This column is no longer needed, and the question is what best to do in order to improve the performance. The main focus in the discussion was about reclaim the size of the column. The first solution which was suggested is to drop the column. It sounds like something that makes sense, or maybe it doesn't. Let's create a sample table with one row, and then I will drop the column and examine the result. Notice that dropping the column did not drop the physical column. It only marked the column as a hidden column using the null as the name of the column. The partition column ID, which is the logical order, changed to a very big number to logically move it to the end. But physical order, the leaf null bit, did not change. The location, the physical location of the column, the leaf offset was not changed. This is only a metadata action while nothing was changed in the table itself. This reminds me, by the way, a story with one of my clients several years ago. I got a support call from a DBA claiming that someone in the company dropped a column in a table by mistake. I always get stories about, it's not me, but someone did it. Anyhow, the DBA explained that they do not have a backup of the database, obviously, and they lost all their data in the column. Now, Microsoft documentation at that time state that this action could not be undone. Is this true? Did we really lost any of the data? Well, the answer is that the official documentation is written for the simple users. A simple user which work only with the logical layer cannot undo this action. But for internals level users, this is a different story. In few seconds, we are going to do it. And after all, you cannot argue with the fact that it can be done when we are doing it. So as first step, I fixed the documentation at that time. And now let me prove it and show you how we can find the missing data. Obviously, first, we need to know what we are looking for. In this case, we are dealing with the simplest data type, which is integer. I will use the function convert to get help in order to find the value on the disk. After convert, I only need to use the binary part. Let's split it into bytes. And then remember that SQL Server store this data in reverse order. So this will go first, then 27, and this is the expected value on the disk. You should already remember the undocumented commands dbcc ind and dbcc page, which we can use in order to read the data on the disk. Voila. We can clearly see that dropping the column did not remove the data from the disk. Here it is in the first location, right after the 4 bytes of the header. This is the reason why dropping a column is fast task. Even if we have a huge table, there was nothing that really deleted. This simply changed the metadata of the table. There is no problem to restore the data since it was not changed on the disk at this point. The conclusion from this solution is that we did not reclaim the space from the disk. Dropping column is not an optional solution by itself. Another solution which was mentioned is to update the value of the column to 0. This makes no sense. Since big int is a fixed length data type, which means that any value will use the same size. It's not matter if it's 0 or 1 million. In fact, this just means that we lost the history of the data, no value, only disadvantage. One of the experts raised an important question or an idea in a way of a question. So, okay, we know that those solutions did not reclaim the size since we did not change the structure of the existing rows. But what about the new rows? When new rows have the same old structure with the position of the column even after we drop the column? The answer is that all rows of the table follow the physical structure, which configured in the metadata. Even if we will remove all the rows from the table, any new row which will be inserted will use the exact same format, including the empty spaces in the middle of the row. Well, if dropping the column or changing the value does not work, then someone suggests changing the column from not null into null. The idea was that maybe this way the server will not occupy the size of the column if there are no data, at least for the future. Well, you can notice that there is no change in the leaf offset, which means that the 4 columns occupied the same location. The only change in the structure is that the column was simply marked as a nullable. This makes sense. Why should a server create all the rows from scratch and copy the entire data of the table? Just for the sake of the meeting, let's show the impact of altering the column from null to not null. This did not took the table to the previous structure. After a alter from null into not null looks like dropping the column and adding another column in place. But it simply done the metadata work and nothing was changed in the table. The column is marked as null and a new column created in the same place in the metadata table. Let's try to change the type of the column to smaller type. This is like a combination of a previous idea. Changing the value without the structure did not help, since this is a fixed data type, but we can change the value and then change the data type from big int to tiny int. Not just that this did not help us, but again, a column is marked as null, but a new one was added for us. There is no change in physical position. This action is only in the metadata. What we have now in the table, it's simply a situation where a size like this became a size like this for the data, and what we have here simply stay empty as part of the row structure. Off topic, let's try to alter from tiny int to a big int. Again, just for the sake of the learning. This action is equivalent to drop column, but not like before. The column did not added only in the metadata in place. This new column was added at the end as a new column. So this is equivalent to drop and create and add new column. Notice that the value of the leaf offset is 52. This column was added after all the other fixed length group. This is very strange behavior, in my opinion. Think about it. We have the place to change the column back to big int because it was big int. We change it to int, and now we take it back to the same place. But this is the way SQL Server works. And this is why we must learn and understand the internals. Knowing what happened behind the skin will help us to choose the right solution and get best performance. So is there an option to add a fixed size column in place of an old one? This is off the topic for the question, but we have to answer it, and the answer is yes. This can be done, as we will see right now, if the column that we drop is the last physical column, then the server can simply add a new column in its place. I'm dropping the last column, which we just created now in the previous test, and I will add another column with different name, which is big int. And we can see that it was added in place of the dropped column. What next? Well, we spoke about what not to do, but our goal is what can we do, and not what we cannot do. In order to clean the table structure after we change the table, we only need to remember to rebuild the table. So dropping the column is a solution, but only part one. Next, we need to rebuild the table. Once you rebuild the table, you can notice how we get a clean and nice table without empty spaces between columns. Until now, I focused on the physical structure of the table using the undocumented system internals views. We examined the logical and physical structure, and we saw that SQL Server uses physical hidden columns behind the skin, but what we did not show you yet is that SQL Server also have undocumented virtual columns. Virtual columns are part of the table structure, and we can query them directly, but they are not physically stored any data in the table. The documented virtual column, which everyone use, called computed columns. Today's session is for advanced user. Obviously, if you are still here after 50 minutes of digging into the internals, then you do not need me to explain to you what is a computed column. Let me just go through the script very fast. I already created the partition function and the partition schema. Let me just create the table and insert some data. And this is one way we can create a computed column, adding it to the existing table. Okay, what is undocumented? There are several virtual columns which we can use, the row dump, physical lock, and lock rest. Physical lock give us the information about the location of the row in a binary format. Lock rest give us the same information, but in a readable format. And row dump give us information about the columns. If you want more practical use example, you can check this post. Here, for example, I'm using the physical lock in order to delete duplicate rows in heap table. In heap table, we don't have an index, and it's very useful to use the physical location in order to have an identification for each row. We have several functions which we can mention. We can use them in order to get the information. For example, if we need to find the partition which each row exists, then we can use the function get rows set ID form row dump. Very long name. This can help us, if we will aggregate the data, to find the scatter of the columns between the partitions. Another function that we can use give us the interpretation of the physical log to a readable format. In fact, this gives us exactly the same information as the first lockerless information give us. A table function that we can use in order to get all the information about the columns. And last, for this demo, we can use another function in order to get the information about the file ID, page ID, and slot ID of each row. When we are speaking about the structure of a table, we need to remember that the table have properties. For example, we have the identity, which is not a column property, but a table property. And there is a simple trick if you want to work with the identity and remove it or add it to existing table. So just go very fast. I create a table with identity, and I will check which page include the information of this table. So you will believe me that what I'm going now to do will not move anything. It is just a metadata task. How we can remove the identity? I will create a new table with the same structure, but without identity property. And now this is the trick. I can use switch. What is switch? Switch basically register the data to a different table. So I can alter the table T and switch the data to the table T1. You can notice that now T1 include the data and T does not include anything, and T1 does not have identity. The only thing that I need to prove you is that the location was not changed. And you can see the same 56 is the number of the page which include the data. The opposite side, if you need to add the identity to existing table, so I will create a new table with identity. And now I can switch to the new table. In this case, I need to configure the identity value that it will start from the last value that we had before. So what I'm using is declare ID. I'm checking what is the last value that we have. I add one more, and then I'm using DBCC check ident. That's it. We have identity on the table. You can see the old table T1 does not include data, but the new table T2 include the data that we had before. You want me to prove you that the data did not change, so let's check the same 56. Last confirm we can do to check that the identity actually work on the new table. So I will add one more row. Voila, the identity was increased. If you need now to use the name of the old table, you just need to do one more step, which is rename of the table. Okay, at this time, we can go back to the first script, which we opened the session with. And now we have the tools to understand what is going here. So let me add the option to drop the table first. And now I can execute the script. As we remember from the beginning of the session, first time we got a table with 5,000 pages. Now let's go to the script itself and see what happened. When column 2 is in the first location, we got a small table. Why? Because in the script itself, I'm dropping column 1. And if column 1 is in the last location, so we know that we can create another column in place. And this is all the magic. When the order of the column was different, then column 3 was added, but after the last column. And I add some data, and that's it. This is all the script. Let's go to the second script that we started the session with. And again, you can notice that first execution, column 2 was the first one. Exactly the same trick. After I add some data to the table, first I drop column 1. So the difference is, or the question that we need to ask ourselves is column 1 is the last one in the set of fixed length column? And if it wasn't the last one, then we got an error. Why? Because now we add another column, char 1, and then we add another column, which is char 3000. If the column wasn't the last one, then when we added this column, we got more than 8 kilobytes in size because this column was added after the last column. But if column 1 was the last one, then when I drop it, I can now add this one in place. This is all the trick. Great, we are just on time and we have last 10 minutes or so for questions and answers in the chat. At the same time, I will summarize the session and present some best practice, golden rules, and tips. So what we have done today, I opened the session with the question, is order of columns important? This is a bit tricky question, which simply gave us a starting point and a closure when coming back to the question after we learned a bit more. We had to understand that SQL Server has an undocumented hidden layer, which I named the physical layer, and it is used by the server internally. Two simple scripts clarified that the order of columns can have a huge impact on performance and even led to errors. It was clear that in order to understand the behavior, we must dive into the internals. For this, we had to use undocumented tools. In the next 40 minutes or so, we checked how the table's physical structure changed behind the skin as a result of different DDL queries executed on the table. We tested the impact of adding and removing primary key, clustered index, non-clustered index, changing the data type of column, changing the properties of columns and table, and more. We saw that changing the table impact the physical structure, and this might leave a lot of unwanted wasted storage space inside the row. Dropping column, for example, did not remove the data from the row and led to unused space inside the row. We can clean the table and reclaim the wasted storage in the rows by rebuild the table. Another option, which I did not mention, is that we can run the command dbcc clean table. If I need to wrap up the meeting with 5 important conclusions, then first of all, it's all under the sentence that understanding the internals directly impact your ability to improve performance dramatically. As an example, we saw the order of columns can significantly affect performance. We saw that dropping column does not reclaim size. We saw that when you create a clustered index, You should remember that using unique will reduce the table size. If you make any change on your table structure, then think about rebuild the table to clean it. And remember that changes of table metadata are always fully logged transactional operation. I hope that you found this session interesting and, more important, practical. The presentation and all the code sample will be uploaded online. I will publish the links on my Facebook profile, and probably it will be published in the event page as well. If you have any additional question, feedback, or you just want to say hi, then you are welcome to contact me on Facebook. Obviously, the chat is still open, so we can still continue here, answer questions. I want to thank the organizers and everyone who took part in contributing to the awesome event. And above all, thank you for joining my session. Please take a few minutes right after the meeting to post your feedback. It is highly important. It gives us the way to understand what we need to do better next time. Have a great day and stay safe. Bye-bye.